In this video, we discuss characteristics of the normal distribution, often referred to as the normal curve. We'll use these characteristics repeatedly when calculating and interpreting statistics. When we think about variability in data, one common form or shape that you'll often see is what's called the normal curve. It's a shape that naturally arises in many situations, particularly when we see some random component to the data. One way to see this is with a truly random process, flipping coins. Let's imagine for a moment that we're flipping two coins over and over and over again and counting how many heads come up each time. 0, 1 head, or 2 heads. Mathematically, what's the proportion of times that we would expect to see no heads, or see just 1 head, or see 2 heads? Mathematically, 25% of the time we would expect no heads. 50% of the time we would expect 1 head, and 25% of the time we would expect to see 2 heads. Given there are only 3 options, 0, 1, or 2 heads, the distribution is not very smooth. What if we flipped 10 coins over and over and over again? Flipping 10 coins, we see more of a shape to the distribution because now we have 11 possible outcomes ranging from 0 heads to all 10 coins being heads. Notice that even though the percentage of times one would expect to obtain 0 heads or 10 heads is very small, it's not 0. We would expect to get absolutely no heads flipping 10 coins about once in 1,000 times. Similarly, we'd expect to get 10 heads in 10 coins about once in 1,000 times. What if we flipped 25 coins over and over and counted the number of heads? Mathematically, this is what we would expect to see. Or 50 coins over and over. Or 100 coins over and over. Notice that the distribution becomes increasingly smooth because we have more and more and more possible outcomes. Now, what if we flip an infinite number of coins over and over and over? The result is now the normal curve. People often describe the normal curve as bell-shaped. In fact, sometimes it's simply referred to as the bell curve. Notice that it's symmetrical, meaning that both sides of the distribution are the same, and it's unimodal, meaning that it has a single mode score. Also notice that the mean, median, and mode are all exactly the same score right in the middle. When we talk about something following the normal curve, we're often talking about real things in the real world. For example, maybe if we plotted the weights of adult male rhinoceroses, we would find that a graph of their weights looked like a normal curve. Or maybe if we plotted the weights of grasshoppers, those weights would look like a normal curve. But at other times when we're talking about something following the normal curve, we're actually talking about something that's a little more abstract. For example, maybe the classroom average reading score for a randomly selected set of third-grade classrooms might be expected to follow the normal curve. Now, hold on to that thought. We'll come back to it in the future when we discuss sampling distribution of the mean, inferential statistics, and statistical tests. But for now, we'll stay a little more concrete. Okay? Now, as all of this implies, whether you're plotting weights for rhinos or grasshoppers, you can have normal curves with very different standard deviations. For example, here are 2 normal curves. Notice the red curve has a smaller standard deviation and the scores are more tightly focused, while the blue curve has a larger standard deviation and is more spread out. But regardless, both curves share some common, extremely valuable qualities. To understand those qualities, you have to remember that this normal distribution can be thought of as a graph reflecting the frequency of different scores in our data. Everyone in the data shows up in that curve somewhere. They have a score on the variable which places them somewhere along the x-axis. And the height of the curve for that value on the x-axis tells us relatively how many people also had that score. The higher the curve, the more people there are with that score. We also see that most scores fall close to the middle, close to that mean, median, and mode. And we can think of all of that area under the curve as reflecting the variety and frequencies of scores for all the people. In fact, mathematically, the area under the curve, all shaded blue here, equals 1 or 100%, meaning that the curve reflects 100% of the data or all the possible outcomes. What's powerful and valuable about the normal curve is that regardless of what the standard deviation is, the distribution of scores in relation to standard deviations is the same. For example, if something follows the normal curve, if the distribution of values for that variable follow the normal curve, 68.26% of the cases will lie within one standard deviation of the mean. We can see it here visually in the shaded blue region. This is the range of scores that are between one standard deviation below the mean and one standard deviation above the mean. Now, remember, the total area under the curve is 1 or 100%, which is just a mathematical way of saying that the distribution reflects the range and frequency of all or 100% of the possible data. The shaded in area is equal to 0.6826 or 68.26% of the total, which is just another way of saying that 68.26% of the cases would fall within the blue shaded area or within one standard deviation of the mean. Similarly, if the distribution for something follows the normal curve, then 95.44% of the cases fall within two standard deviations of the mean. Again, that's 95.44% of the data would be somewhere between two standard deviations below the mean and two standard deviations above the mean. Finally, what about three standard deviations? For things that follow a normal distribution, 99.74% of the data will fall within three standard deviations of the mean. Theoretically, there are still a small percentage of cases that are even more than three standard deviations above or below the mean. Just not very many. In fact, only 0.26% of the cases would be either three standard deviations below the mean or three standard deviations above the mean. It's so small here that it doesn't even show up on the graph. We've used the red dashed lines to point to three standard deviations below and above the mean. So this wraps up our conversation on the normal curve. I should note that there are other types of distributions that we'll see in nature and in research. Many things don't follow the normal curve, but we do use the normal curve a lot, and in statistical analyses, you'll see it showing up regularly. Plus, the general principles that we've discussed, area under the curve reflecting percentage of cases or expected cases, is a fundamental idea that we'll be using in statistical analyses.